Buddy. Our next talk will be by Wei Lin, and he will talk about building a distributed system with Celery on Docker Swarm. Please give him a warm welcome.
Hi, everyone. I'm very glad to give this talk here. My name is Wei Lin. I'm from Taiwan. Due to my work experience, sorry. It's now responding. Okay. Due to my work experience, I'm specialized in strategy planning, techniques, and tools. One of which is coding, of course. And I believe we share a common interest in Python. Sometimes we will encounter CPU-bound problems. You may want to use extra computers and CPU power. For example, build a cluster of 100 computers like this to deal with the CPU-bound problems. But the question is, how do you drive this cluster? What's the framework or tools you can use to drive a cluster of 100? Sorry, I don't know what's going on here. Oh, it's what's the framework and tools you can use to drive this cluster? And on the other hand, sometimes you need to build a distributed system like this, because the scale of the system or the network is not stable. So you need to separate the controls, distributed the control into many sites. So you need to build a distributed system. So what can you use? What kind of framework you can use to build a distributed system? Talking about distributed system, recently we have many emerging techniques and paradigms like microservices, serverless computing. They are all distributed. But don't forget, your brain is also a distributed system. The brain is composed of many neurons. They seem to be independent, but actually they are connected, massively connected by a huge network to form an elegant system. So if we are trying to build a distributed system, why not starting with building an artificial neural network using 6 different computers? Each computer represents neurons. For example, a computer represents a parallel row, like for neuron X, and another computer parallel row for neuron H1. So the first question, if you want to build this artificial network, mimic this artificial neural network, is that how can we communicate between neurons? We can write a pair of circuit programs to send and receive message or information between neurons. But you will encounter many problems, because sometimes the network is not stable, the nodes is dead or too busy to respond, to be responsive. So you need to add some mechanism for like a timeout or retry. It's very troublesome. So why don't we use the existing framework for the communication between neurons, between machines? For example, the Celery is a very famous, very powerful distributed test queue framework. Why don't we use Celery to communicate between neurons, between machines? But Celery is a queue-based framework. So there will definitely be a queue in between those machines. But that's okay because we can send a message, for example, the neuron X, to send a message to a particular queue. We call it queue H1. And then we can assign or tell the neuron H1 to pick up the message from the particular queue. So they can communicate to each other, with each other, indirectly through the queue. So let me talk a little bit more detail about the Celery. In Celery, there are three main parts. On the left-hand side is the producer. In the middle is broker. And on the right-hand side is the consumer. The producer sends out the message. The producer sends out a message to the broker. Broker, you can think broker as like a post office. In post office, there are many mailbox, right? So in broker, we have many queues in the broker. They are all managed by the broker. Just like we have many mailboxes in the post office. And the right-hand side, we can assign a particular worker to attend or listen to a particular specific queue. So the whole sequence is that the producer sends a message to the broker, and the message will be routed to a particular queue. And some assigned worker will pick up the message from the queue. So what's the coding level of details about to send out a message? On the computer where the producer is at, we just need to execute some lines of code like this. First, we load the module, the definition of the function or whatever, the module, the code module, and we instantiate a Celery object. And we use this object to load the config file. And what's in the config file is most important. There are some major points in this config file. First is where is the broker? The broker address, the network address of the broker. Also the type of the broker. Celery supports many types of the broker, like Redis or MeshMQ. And the second most important point is the code definition we need to load in order to send out a message. And the third part is the design of the communication channels. We can divide the communication space into many channels by defining the queues, different queues. Each queue has a name and is associated with exchange. Exchange is who is responsible for routing the message. And also each queue, like a mailbox, has a routing key. It's like an identification or a key. The message is routed accordingly. So we load the config file. Then because we also loaded the code module we need, so we can now send message like this. First, in the code module, we have a definition of function definition like kick, but it's also decorated by a Celery.task function. So something changed inside this function. So we can use kick. There are many syntax in Celery we can use to send out message. I use two type of syntax. First is a kick, apply async, and parameters. And the second is kick, apply async, the neuron parameters, and additionally, there's a routing key equals neuron H1. The first type, without assigning a routing key, the message will be sent to the broker and be routed to a default queue. And the default queue is listened by many workers. Depends on what you need, how many you need. And the second syntax with routing key, this type will be, the message will be sent to a particular queue according to the routing key. The first type of first syntax is typically used in parallel computing. The second syntax is typically used in concurrent computing. And what's the content of the message sent out? It's just like this, very simple. First is UUID, whatever is generated. It's not very critical because it's always unique. And the second part is the task. We send out the message with the name of the full name of the function. In this case, it will be the celery.task.kick. And the third and the fourth was they are the parameters. The most important part is the routing key. Here, in this case, is the neuron H1. When the broker receives the message like this, the broker will route the message according to the routing key in the message. It will look for the same routing key in the communication space. Look for the corresponding queue. In this case, because the routing key in the message was the neuron H1, so the message will be routed to the neuron a queue named neuron H1. So the first part, this is the first part, how a producer send out on a coding level, send out a message to a particular queue. The second part is how do we assign a worker to attend, to listen to a particular queue and pick up a message from the queue and execute the queue, the code. It's very simple. Just like we need to only execute a command like this on the computer where the worker is at under the shell. Like we just said Celery.worker. It means we want to initiate a worker process. And this worker process has a name. It's called neuron H1. And this worker process only listens to a queue neuron H1, a queue named neuron H1. And so how does a worker, the worker is assigned to listen only to queue neuron H1. But how does it know where the broker is? The producer know where the broker is, but how does the worker know where the broker is? Because we also load the IoT module, IoT package. We execute this command under this working directory, and it will look beneath this working directory to find an IoT package, and this package, Celery by default will look for a module named Celery.py, and in this Celery.py there is some code, lines of code. First, we initiate a Celery object. Instantiate a Celery object, and we also load the very same copy of the config file. So in this same config file, with the producer, same with the producer. There's an address for the broker. So the worker now also know the address of broker. If you can find a broker, you can find the post office, you can find a queue, you can find a mailbox. So the worker now is capable of look up in the queue in the mailbox to pick up message and do whatever you need to do. Okay, and in the message sent to the broker, there's only a full name of the function. How does the worker know the content of the function, the code of the function? Because in the configure file, we also load the code module. It's the same configure file, so there's a nice saying import iot.neurons. It will look under this package. Look for this. It will load this neuron.py module. So now the worker know the definition, the content, the code content of the message, the full name, the function name corresponding to. So we are saying that we are going to build a artificial neural network of 6 neurons. Do we actually need 6 different computers? No, because because we have Docker, we only need 1 computer. Why? Because in Docker, for the mechanism of Docker, in a single host, in a single physical computer, we can run many containers. Each container, if you look inside, it's just like a very alive Linux operating environment. So why don't we execute those code for the worker inside this container? So we can have 6 or maybe many more worker instance inside on a physical computer. How? Because it's very simple. Just when we are going to run a container from an image, like this one, we run a container from this image, and we run this container with a host with a name neuron h1, and host name also equals neuron h1. And when we run this container, we initiate this container, there's an opportunity to initiate some code inside this container. For the opportunity, we just execute the code we need for the worker. Like this one. Celery, remember? Worker, we initiate a worker process, and it only listen to a queue named neuron X. So this container has a name neuron X, and also a host name neuron X, and it has a Celery worker process running inside, and this Celery worker only listen to a queue neuron H1, neuron X. Sorry. It's a corresponding is one-to-one relationship. So in this way, we can deploy 6 containers onto a single physical machine. In this case, I want to prove it, they are actually distributed. So I deploy 6 containers onto 2 physical machines. In this way, we can deploy 6 containers. Each has a Celery worker process running inside to establish an artificial neural network of 6 neurons onto 2 physical machines. And if this container, this neuron want to send message to this container, this neuron X want to send message to a neuron H1, it just need to say kick apply async routing key equal neuron H1. And if there's a return command inside the function, you need to retrieve the some data or some result from the remote. You need to just add a get command at the end. The data will be returned from the H1 to back to the neuron X. So what's the use? What's the is there? Can we generalize some design pattern with Celery and Docker? I think let's look into the mechanism of Docker. In Docker, we have three main states. First, we write some script to define in a Docker file. And we use this Docker file to build a Docker image. And we use this Docker image, we run this Docker image to establish some a Docker container. And let's also look into a Docker file. What's in a Docker file? In a Docker file, we have from some base image. So we can think, if we think object-oriented, we can think from as a mechanism to inherit. Whatever what's capable in this base image will be inherited just by adding a from command into this image. And in the definition of the Docker file, in the Docker file, we also define whatever software we need to install. So we can install some additional software, or we can copy some data into this image. So we can think a Docker file as a mechanism of to encapsulate. What's the point? Because we have this inherent encapsulate, so we can think whatever image built from this Docker file, we can think a Docker file, a Docker image as a class, and we instantiate the object from class, just like we run image to establish container. So with Docker Swarm, we can deploy any container we need, any container we want onto any physical machines in the Docker Swarm cluster. For example, we have 3 containers. One is in Tokyo, one is in New York. And if there's a Celery worker process running in the container, then it's capable of receiving message. Then we can use Celery to communicate between those new containers. For example, if we want to send a message from the Tokyo to the New York container, we just say, do something, apply async routing key equals host ny. And if we want to retrieve data from the remote, we just add a get function command. In this way, we can actually do the remote procedure call like this. So if you are familiar with the UML, this is an example of a sequence diagram. I think almost every system could be described with a sequence diagram. And now the sequence diagram is based on Celery and Docker Swarm with distributed nature. It may mean that every system can be converted to a distributed version of the system. So back to the first question we asked at the beginning, how do we build a distributed system. With Docker Swarm and Celery, I think we can fall back to the basic principle of object-oriented analysis and design. For each use case, we draw a sequence diagram, and after you're done with every use case, then you have a bunch of sequence diagram, then you will know what kind of which function or data to be encapsulated inside a container. So what can be a container inside a container? It all depends on your need. A message, in this case, a message was received by the worker, a Celery worker process, and corresponding Python code, a function will be executed. And it depends on your need. You can do whatever inside the Python function code. For example, to initiate another GPIO, or do the REST API to initiate to trigger a service, a Node.js service, or initiate another TensorFlow program, all inside a container. It all depends on your need. So, back to the second question we asked at the beginning, how do we build a parallel computing cluster? It could be done with Celery and Docker Swarm, I think, because I think the parallel computing is a subset of distributed computing. If we can arrange the information or workflow like this one, then we can also arrange the information or workflow like this one. This is concurrent computing, and this parallel computing. I think it could be done in the same way. So if you want to deploy a parallel computing cluster, you just, with Celery and Docker Swarm, you just need to initiate a container and scale up to a number you need, and deploy among the Docker Swarm cluster. And when the Celery workers are ready, then you can start send out a message for the worker to pick up and do whatever they are going to do, need to do. But in this case, there's a drawback and limitation, because Docker Swarm relies on a root level passwordless SSH mechanism. This will certainly limit the scale of your cluster, because it always I think it always means you need to own those machines in your cluster. But there's a better way. We can follow the paradigm of SCTI at home, which is a very famous distributed project, parallel computing project. And we can do the same thing by just running a container, Docker container. We just need to run on a client, just run a container. We just say Docker run, and this container, that's all. Why? Because we encapsulate everything we need inside this container. The config file, the code module, the whatever we need inside this container. And there's also an opportunity to initiate. We have a default initiate command inside the container. If we run this container, run this image to HTTP container, the default initiate command will be executed, which will be the Celery worker something to initiate the worker process. So when we run this container, the worker will be boot up and start look because there's a config file. Oh, okay. Sorry. Because there's a config file, so there's a broker address inside, so the worker will know the address of broker. It will start working. So the summary is that I think this syntax is very easy to use, and the configuration file is not very complex. And the advantage of a distributed system is they are decoupling and shared and load balance. And there's also a caution inside at the end of this PowerPoint. Please take a look at it. Thank you very much.
All right, thank you very much, Waylin. Unfortunately, we ran out of time, so we won't have time for Q&A right now, but I'm sure he will be around and you can ask him afterwards in the hall. Next up is a long break, and we ask you all to please, if you can, go to the first floor because we want to take a picture of all the attendees, if that's okay. And if you do so, we will reward you with cupcakes. Thank you.